Hi everyone, our lesson today is 2 color balls probability with ordered sampling of 2 and with replacement. We have the following problem to solve. An urn contains 12 blue balls and 8 red balls. Without looking, we are withdrawing according to the following rules. 1. We withdraw 2 balls. We register the result of the withdrawals in order. And after each withdrawal we return the ball to the urn. Now the question is, what does the sample space consist of? So let's have a look. We have this urn here with 12 blue and 8 red, and we have a group of red and a group of blue. So coming back to the problem, what does the sample space consist of? We have the blue group from 1 to 12 and the red group from 1 to 8. We can put all of them in one group. And now we are withdrawing 2 objects in order. So we can withdraw, let's say, B4 and then R3, or B7 and B7. We can repeat the withdrawal because we are withdrawing with return. We are returning the object to the urn. So since we are withdrawing 2 balls with return, the sample space consists of sequences composed of 2 symbols with different letters or with repeated letters. With different letters such as B9, R5, or with repeated letters such as B12, B12, etc. So we can say that the sample space consists of sample point of size 2. And therefore R is equal to 2 for the whole problem questions. So what is the number of elements in the sample space, or what is the number of all possible outcomes? We have the urn here with 2 sets of balls R and B, and we can combine all these balls into 20 balls numbered from 1 to 20, which means we can map all these objects into numbers from 1 to 20. So now we have a 20 object. Going back to the question, what is the number of elements in the sample space? We have a 20 object, and we can write them in one group, and we can map them as numbers from 1 to 20 as we see here. And now what we are doing, we are generating sequence of 2 objects out of the 20 objects we have under the 2 conditions, which are order and replacement. So we use the formula of permutation with replacement for a 20 object taken 2 at a time, which is n to the power of r, which is 20 to the power of 2, which is 400, equal to 4. So now we have 400 sequences in the sample space, or we have 400 sample point in the sample space. Or we can do that using the multiplication principle. We write the table with ordered withdrawal. For the first withdrawal we have 20 objects to withdraw from, and for the second withdrawal we have 20 objects. And now the number of sequences in the sample space is their multiplication, which is 400. So we have 400 possible outcomes, which is the number of elements in the sample space. So now before we go into the probability issue, we have to remember a few things about disjoint sets. What is a disjoint set? So 2 sets A and B are said to be disjoint if they have no elements in common between them. So now let's assume that A and B, A is 1, 2 and B is 4, 5, 6, 7. We find that there is no any mutual number between them. So their intersection is a null group. So these are the disjoint sets. Now we have to remember the axiom of disjoint event in probability, and this axiom states that for any two disjoint event A and B, we have their union is equal to the probability of the first set plus the probability of the second set. And we can generalize that into more than two sets. So the probability of all this union is equal to the probability to the sum of probability of each set. Now we are going to consider the following event. The event which is BR, withdrawing blue object first and red second. RB, which is the contrary, withdrawing red first and blue second. BB, which is withdrawing blue object first and blue object second. RR, withdrawing red object first and red object second. But how did we come up with this elementary event here? The answer is we use the tree diagram. So here's the tree diagram. We may get either blue or red, and if we get blue, let's say we are getting again either blue or red. So the number of possible outcome for blue and red is blue blue, blue red, red blue, and red red. So from this tree we can find that we have mainly 4 elementary events which we have already defined. So going back to this question, considering the events, these are elementary events and we define them in order to define more complex event later on, as we will see. But this event, if we combine them together, if we get their union together, we are going to get the sample space. So these events are disjoint, which means that there is no any common element between BR or RB, RB and BB, and so on. And their union, if we add the element of these subgroups together, we are going to get the sample space itself. We are going to make sure of that later. And so we call these subgroups as partition in the sample space. What is a partition? It's as if we have a house containing all these elements of the sample space, and we put partition in between them. We divide them into subgroups, and their union will create again the sample space. How many blue and red balls can be withdrawn one after the other? So we can withdraw the blue object in 12 ways and the red object in 8 ways, and therefore their multiplication is 96, which is the number of ways of blue and red. Or we can use this table. We write the event in order, withdrawing blue ball first and withdrawing red ball second. So the number of ways of withdrawing the blue object is 12 ways, and the red object 8 ways. Their multiplication 96 is the number of ways of withdrawing blue and red. Now the question is, what is the probability of withdrawing blue and red objects one after the other? So what is the probability of blue first and red second? It is the number of elements in the event blue-red divided by the number of elements in the sample space itself, which is 96 divided by 400, which is 6 divided by 25, or 0.24. So what we conclude from this number, 6 divided by 25, that if we repeat this experiment about 25 times, it is expected that we are going to get 6 blue and red withdrawal. That's what it means. The other question is, how many red and blue balls can be withdrawn one after the other? So this is the opposite of the previous question. We can choose red in 8 ways and blue in 12 ways. So their multiplication according to the multiplication principle is going to give us the number of ways of occurrence of red and blue balls in order. We can use again the table of event or the event table. The number of way of withdrawing the red object is 8, and number of way of withdrawing the blue object is 12. Their multiplication is 96. Again, we can compute their probability, the probability of event red and blue. It is 96 divided by 400, which is 6 divided by 25, and which is equal to 0.24. So what does 0.24 means? It means if we repeat this object around 100 times, it is expected that we are going to get a 24 withdrawal of red and blue. How many blue and blue objects can be withdrawn one after the other? So the set of blue objects is from 1 to 12, and we have here 12 objects. So we are generating sequence of 2 objects out of the 12 objects here, or 2 letters out of the 12 letters under these 2 conditions, which is order and replacement. So in such case we can use the permutation formula with replacement for 12 objects taken 2 at a time, and this is going to be n to the power of r, so 12 to the power of 2 equal 144. So we have 144 ways of picking blue and blue object in order. Or we can use the table of events. So we have here the first event withdrawing blue object, and second event again withdrawing blue object. So the first event happen in 12 way, and second event can happen in 12 way. So their product is 144. Now what is the probability of withdrawing blue and blue one after the other? We divide the number of possibilities of blue and blue over 400, which is the number of point sample in the sample space, and we get 0.36 blue and blue. So another question, how many red and red objects can be withdrawn one after the other? So we have 8 red times 8 red, or we can use a permutation formula with replacement. We have here 8 objects, and we use the permutation formula with replacement of 8 objects taken 2 at a time. So this is 8 times 8 equal to 64. So we have 64 possible outcome of withdrawing red and red in order. Or we can use the table of event. So here we have withdrawing red in 8 ways and withdrawing red in 8 ways. 8 times 8 is 64. So what is the probability of withdrawing red and red objects one after the other? We divide the 64 over the 400, and we get 0.16 of red and red. But before we continue, we have to make sure that the union of these elementary events is going to give us a sample space. And how do we do that? We write the corresponding outcome of each event. So for event BR, number of possible outcome is 96, for RB is 96, for BB is 144, for RR is 64, and we check if their sum is equal to the number of elements in the mother sample space. So if we add them together, we get 400, which is the number of elements in the sample space we computed before, and that means that these events are disjoint events. So this 400 is the number of all possible outcome, or number of sample space element, or number of sample space points, or total number of the generated sequences in the sample space, all mean the same. So now we are going to create complex event out of the elementary events. So the question here is, what is the probability of drawing two balls of the same colors? So we are either withdrawing blue or red. Both of them are elementary events, and both of them are disjoint event, which means the probability of withdrawing two balls of the same color is the probability of withdrawing blue or red, which is the union of both of them, and that means it's equal to the probability of blue plus the probability of RR, and the reason why they are two disjoint events. So we add this probability together and we get 0.52. Another question, what is the probability of withdrawing two different color balls? So now we are going to withdraw either blue and blue-red or red and blue, and these events are disjoint, so their probability, the probability of event blue-red or red and blue is equal to the probability of the union of blue-red or red-blue, and that is the probability of blue-red plus the probability of red-blue, which is 0.48. Again, what is the probability of withdrawing blue or blue-red? So this is a question. This is a complex event created out of these two elementary events. The two elementary events are disjoint. So probability of BB or RB is equal to the probability of BB plus RB, which is 0.6. So what is the probability of withdrawing RR or RB? It's exactly like the previous question. The two events are disjoint, and their probability is the probability of red plus probability of red-blue, which is 0.4. And now we have this interesting question, what is the probability of withdrawing at least one blue ball? So we can withdraw blue-red or red-blue or blue-blue. So we can see how this event here is composed of three elementary events, and these events are disjoint, so their probability of blue-red or red-blue or blue-blue is the probability of their union, and that is equal to the probability of each event added to the second event to the third event, and we get 0.84. So now, what is the probability of withdrawing at least one red ball? So this is also a complex event composed of three elementary events. So it's either withdrawing red and blue, or blue-red, or red-red. And so the probability of this event is equal to the union of these three events, which is equal to the sum of each individual event, and which is equal to 0.64. Now we notice that the probability of withdrawing at least one blue ball is bigger than the probability of withdrawing at least one red ball, and the reason is the number of blue balls is higher than the red balls in the urn. So the final question is, what is the probability of withdrawing blue-blue, red-red, blue-red, or red-blue? So if we notice that the sample space is composed of the union of all these events, so that means the probability of this event, the probability of this complex event is going to be 1. Because it's the probability of the certain event of the sample space S. We can make sure of that. We can add all these probabilities together of the 4 events, and we are going to get 1. Thank you for listening and have a good day.